All right, buckle up, everybody, because today we are diving deep into a theory that says the stability of atoms could actually be tied to a hidden wave pattern right in the fabric of space. It's called Fibonacci SMF RVS. And yeah, I know what you're thinking. What in the world does that even stand for?
Well, it stands for Fibonacci, which is kind of like the famous Fibonacci sequence, but with a twist. And then SMF, which stands for subtle magnetic fields. And of course, RVS for the relative vacuum of space.
Catchy.
It is all laid out in these super interesting theoretical papers by L.S. Larkey.
Hmm.
And let me tell you, they propose something really radical.
All right, so I think we all know that some atoms are like insanely stable, like helium-4, right? 2 protons, 2 neutrons, and it pretty much lasts forever. And the classic explanation for this that we all learned back in school is the shell model.
Right.
Protons and neutrons filling up those energy levels, kind of like seats in a stadium.
Exactly. Full shells equal maximum stability. And those are the magic numbers.
Yeah.
2, 8, 20, 28, 50, 82, 126. But Fibonacci SMF-RVS says, hold on a second. There might be a much, much deeper reason for those numbers.
I've always felt like just saying filled shells always felt a little bit like we were kind of sweeping some deeper mystery under the rug. You know what I mean?
Well, get ready to lift that rug up because Fibonacci SMF-RVS is basically saying those magic numbers aren't just about filled shells. They're actually points of resonance within a fractal wave pattern that, get this, permeates the vacuum of space itself.
Whoa, wait. Fractal wave pattern. So like those crazy mesmerizing patterns you see all over in nature, but somehow woven into the actual fabric of space.
You got it. Like, imagine the universe is this giant cosmic symphony, and all those magic numbers are representing the harmonious notes, the ones that just really resonate.
Okay, now I'm really intrigued.
So when an atom's protons and neutrons, they hit a magic number, they're basically vibrating in sync with this like underlying wave structure. And that is where the Fibonacci sequence comes in.
All right, so remind me, how is the Fibonacci sequence different from the Fibonacci sequence? And how does it all fit into this whole thing?
Okay, so we all know Fibonacci, right? It's all about adding the previous 2 numbers to get the next one. So 1, 1, 2, 3, 5, 8, and so on. But Fibonacci, it adds this like really fascinating twist. It still involves the previous numbers, but it incorporates prime numbers in a very specific way.
Prime numbers, those like quirky numbers that are only divisible by 1 in themselves, what do they have to do with like the stability of atoms?
Well, that's the million-dollar question, isn't it? But here's the thing. Prime numbers, they kind of pop up in these unexpected places in like nuclear physics. So when you use the Fibonacci sequence to calculate potential numbers of protons and neutrons, you get these peaks of stability, these magic numbers that the traditional models, they kind of miss.
So are we saying there could be like even more magic numbers out there than we thought? Numbers that could point to even more stable isotopes?
That's exactly what it implies. And what's even wilder is that some of these new magic numbers that this predicts actually correspond to isotopes that we already know exist.
No way. So we're not talking about like some hypothetical atoms in a far-off corner of the periodic table. We're talking about elements that we already know and use.
Right.
That's wild. So what are some examples?
Well, you got things like nitrogen-14, sulfur-34, zirconium-90, and Fibonacci SMF-RVS suggest that these isotopes might be way more stable than we currently realize because their total number of protons and neutrons hits those special points of resonance in the wave pattern.
Okay, so this is blowing my mind. So if this theory is right, then these like seemingly ordinary elements, they might actually hold the key to unlocking a whole new understanding of physics.
It is definitely a possibility. But, it's not just about finding these new stable isotopes. Fibonacci SMF-RVS makes an even bolder claim.
Oh.
It says that if we can actually tap into this fractal wave pattern, we could potentially control the way atoms decay.
Hold on. Control the way atoms decay? Isn't radioactive decay like a fundamental law of nature? I thought that was pretty much set in stone.
Well, yeah. That's what we've always thought. But remember, we're talking about a potential new understanding of the vacuum itself. Fibonacci SMF-RVS suggests that this vacuum, it's not just a passive backdrop, it's an active player in the game.
Whoa, so instead of just accepting that some atoms are like destined to break down over time, we might be able to actually influence that process.
That's the idea. If those magic numbers really are points of resonance within this fractal wave pattern, then the isotopes that fall, like off-node, so to speak, they'd be more susceptible to decay because they're not quite vibrating in sync with the cosmic symphony.
Okay, I think I'm starting to get it. So the key to influencing this decay lies in those subtle magnetic fields, the SMF part of the theory.
You got it. The theory suggests that by applying these, like, very carefully tuned magnetic fields, we could potentially nudge those off-node isotopes closer to a point of stability.
Okay, I'm trying to like wrap my head around this. So we're essentially talking about using magnetic fields to like tweak the way an atom interacts with the very fabric of space.
That's it. Think of it like fine-tuning a radio. You adjust the dial, you change the frequency, you pick up a different signal. And in this case, we'd be tweaking the magnetic field to change how the atom resonates with that underlying wave structure.
That is a wild concept. So how would we even begin to test something like that in the real world? Do we need like some crazy, super sophisticated magnetic field generator?
It would definitely require some cutting-edge tech, that's for sure. We need an environment that is like completely controlled, shielded from any kind of external electromagnetic noise. Think like a special chamber with coils that can generate super precise magnetic fields.
And inside this chamber, we'd put a sample of a radioactive isotope, something with like a really well-known half-life, so we have a baseline to compare it to.
Exactly. Cesium-137, cobalt-60, even some of those short-lived medical isotopes. And then we carefully monitor the sample as we apply these, subtle magnetic fields and look for any changes in its decay rate.
So we'd be looking for signs that like the half-life is either speeding up or slowing down, or even any changes in the type of radiation it gives off.
Precisely. But here's the catch. We can't just go blasting these isotopes with any old magnetic field. We need to generate fields that perfectly mimic the patterns predicted by the Fibonacci sequence.
Because it's all about resonating with that underlying fractal wave pattern?
Exactly. It's like you're trying to unlock a door. You need the right key. You need the right combination to make it work.
Okay, so this is sounding incredibly complex. We've got our isotopes, our super shielded chamber, and our like custom designed magnetic fields. So what's the biggest challenge with all of this?
Honestly, one of the biggest hurdles would be making absolutely sure that any changes that we see are actually caused by those subtle magnetic fields and not some other like random external factor. We can be talking about super small effects here. So we need to be incredibly meticulous in how we design this experiment.
So like rigorous controls, triple checking all the data, and ruling out every other possible explanation for anything we see.
Absolutely. We need to be as certain as we can possibly be that we're not being fooled by like temperature changes or even tiny glitches in the instruments themselves.
And what if, like, against all odds, we actually see something? What if that cesium-137 starts, like, decaying faster or slower than it should?
Well, that would be like hitting the scientific jackpot, wouldn't it?
Yeah.
It would be a strong indication that we are onto something truly groundbreaking.
It would mean that this whole Fibonacci SMF RVS theory, this idea of a living vacuum and fractal wave patterns, it might actually be real.
It would suggest that there's a whole layer of reality, a fundamental force that we haven't even begun to understand.
It would mean that this whole Fibonacci SMF RVS theory, this idea of a living vacuum and fractal wave patterns, it might actually be real.
It would suggest that there's this, like, whole other layer of reality, a fundamental force that we haven't even begun to understand.
Okay, my brain is officially doing backflips at this point.
Mm-hmm.
If what we've been discussing is even, like, remotely true, the implications are just massive. But let's take a step back for a second. For our listeners who are maybe still thinking, this all sounds like something straight out of Star Trek, why should they care about this theory?
Because if Fibonacci SMF RVS is even partially right, it could fundamentally change how we interact with the universe at like the most basic level. We're talking rewriting textbooks, reassessing everything from like how we deal with waste to how we produce energy.
Okay, so let's break those implications down a bit. We talked about nuclear waste earlier. How could this theory change how we deal with that?
Okay, so imagine a world where we could actually speed up the decay of radioactive waste safely and efficiently. Instead of storing it for thousands of years, we could potentially reduce it to harmless materials in like a fraction of that time.
That would be incredible. No more worries about long-term storage solutions, leakage risks, or like the potential for environmental disasters.
Exactly. And think about what this could do for medicine.
Oh, yeah.
We could like fine-tune the half-lives of medical isotopes and develop more targeted therapies. Imagine delivering radiation treatment right to a tumor with almost no impact on the surrounding healthy tissue.
We're talking revolutionizing cancer treatment, potentially saving countless lives, all because we learned how to tap into this hidden wave pattern in the universe.
It's pretty amazing, right?
It is. It really is.
And honestly, those are just the applications we can imagine right now. Who knows what other possibilities might be out there once we really start to understand and harness this potential new force of nature.
It's almost too much to take in. It sounds like this one theory could, like, unlock solutions to some of humanity's biggest challenges.
It definitely has that potential to be transformative, yeah. But like with any powerful new technology, there are always risks to consider.
Okay, so what kind of risks are we talking about here?
Well, imagine if this knowledge fell into the wrong hands. If someone figured out how to use this understanding of atomic decay, but for, like, malicious purposes,
Oh, wow.
the consequences could be devastating.
So while this discovery could lead to these incredible advancements, it's crucial that we approach it with caution and responsibility, making sure that it's used for good and not for harm.
Absolutely. The ethical considerations surrounding a discovery of this magnitude would be huge.
Well, I think it's safe to say that we've covered a lot of ground today. We went from those seemingly simple magic numbers to fractal waves, living vacuums, and even the possibility of actually manipulating matter at its core.
It's a pretty wild ride, huh?
It really is.
It just goes to show how powerful scientific inquiry can be. Like a single question, a little spark of curiosity. It can lead you down these paths you never even imagined.
So for our listeners who might be feeling a little overwhelmed by all of this, what's the one thing you hope they take away from this conversation?
I'd say just keep asking questions. Keep exploring. The universe is full of mysteries waiting to be uncovered. Don't be afraid to challenge what we think we know and explore ideas that might seem impossible at first glance.
Because sometimes those seemingly impossible ideas are the ones that unlock a whole new understanding of ourselves and the world around us. I think it's safe to say we've covered some pretty mind-blowing stuff today. We went from magic numbers to fractal waves to a living vacuum, and even the possibility of, like, changing the very essence of matter.
Yeah, it's been quite the deep dive.
It really has. So for our listeners who are maybe still trying to wrap their heads around all this, what's the one thing you really hope they take away from this conversation?
Honestly, I'd just say keep asking questions. Never stop exploring, you know? The universe is full of these incredible mysteries that are just waiting for us to uncover them.
That's true.
And don't be afraid to, like, challenge what we think we know and explore those ideas that maybe seem a little impossible at first glance.
Yeah, because sometimes those are the ideas that lead to, like, the biggest breakthroughs, the ones that completely change our understanding of the universe and everything in it.
Absolutely.
Well, I want to thank you so much for taking us on this incredible journey into the heart of Fibonacci SMF RVS. It's been an absolute pleasure.
The pleasure was all mine.
And to all our amazing listeners out there, keep those minds curious. And, as always, happy deep diving.